Hey folks, Ms. Gosling here. In this video, you're going to learn about gravitational fields. By the end of the video, you'll be able to solve problems using the gravitational field equation. You'll also know what that equation is and what each of its component parts mean. So let's go ahead and get started. Now, you've already learned about what the equation is for a gravitational force. We've also talked very briefly about what a field is and what defines a gravitational field. So in this video, we're going to be getting into a little bit more of that nitty-gritty about how we calculate gravitational fields and then how we can use them to make some of our math problems a little bit easier. Now, a gravitational field is essentially the amount of force a 1 kilogram object would feel at a specific point in space. So essentially what a gravitational field is it's how strong the gravitational attraction is towards an object at a given point in space. Now, as we know, gravitational forces are actually dependent on the mass of the object that is being attracted as well. So, if we have, for example, the sun and the earth, the gravitational force between them, which I'm going to go ahead and use Fg to represent, is dependent on the mass of both the sun and the earth. But the gravitational field strength of the sun, which I'm going to call little g, the gravitational field strength of the sun at the point in space where the earth sits is dependent only on the mass of the sun. And what that's useful for is we can put any object at that point in space, and as long as we know the mass of the object and the gravitational field strength, we don't have to go through the whole ugly gravitational force calculation. We can simplify things a little bit. So let's go ahead and just talk briefly about where our equation for gravitational field comes from. Because that equation is up in the left-hand corner here. We've got our gravitational field, little g, and that is equal to our gravitational force divided by the mass of the object that we're putting in the field. And I'm actually going to write that in blue because in our picture to the right, the sun is the object we're putting in, or the earth is the object we're putting in the field. Now, a couple things that I want to bring through here. First, I want to go ahead and just explain how we go from that middle equation, this guy right here, to the one on the right. So we know that our equation for little g, we're defining little g as our gravitational force divided by the mass of an object at the mass of the object experiencing that force. And we know that we can write our gravitational force as g times the mass of the object that is, we're going to say, creating the force, even though, again, we know that both objects are causing this gravitational force to happen. But we're saying it's equal to big G times the mass of the object whose field we're interested in, divided by the mass of the object we're putting in the field, divided by the distance between them squared. So that's expanding out the numerator of my fraction. And then my denominator remains just little m, the mass of the object that we have put in that field. So when we simplify that, that gives us g times m times little m over r squared times another little m. So those little m's cancel, giving us that little g is equal to gm over r squared, where big G is our gravitational force constant, m is the mass of the object creating the field. And I want to really make sure that I emphasize this. So again, big M is mass of object creating field. And I'm defining little m here as the mass of the object in the field, which I've already written over here. I'm going to go ahead and just add that extra arrow. And that is going to be divided by the distance I am from the object creating the field. So distance I'm away from big M, the mass of from the mass creating the field. Now, last thing I want to mention, why gravitational fields are useful. Say that we know little g at a specific point in space. So for example, on Earth, little g is 9.8, which is our acceleration due to gravity. So first of all, we know the acceleration that an object will have due to the gravitational force, assuming no air resistance. Second, if we know that the mass of the object being put in that field. So for example, if I know that I have a mass of 50 kilograms, then it's really easy to find out the gravitational force acting on me, because the gravitational force acting on me is just 9.8 times my mass, or little g times my mass. So the gravitational field at that point in space times the mass of the object put in that field. So let's go ahead and look at an example. The asteroid Ceres, I don't need to highlight that, I don't know why I did. The asteroid Ceres has a mass of 7 times 10 to the 20th kilograms and a radius of 500,000 meters. What is the gravitational field at the surface of Ceres? So we've got our asteroid Ceres, and we know that we are looking at this distance here, and we want to figure out what little g is. Now, I do want to mention, let's go ahead and just run through this problem, and then we'll talk a little bit about why we bother with gravitational fields. So we are given the information that the mass of Ceres is 7 times 10 to the 20th kilograms, that its radius is 500,000 meters, and that its gravitational field, and that big G is 6.67 times 10 to the negative 11th. Okay, so continuing forward, our unknown is little g for Ceres. So our gravitational field at the surface of Ceres. And I know that that is given by the equation G equals gm over r squared, which means that I'm ready to go ahead and sub and solve. Now I know I need to use this equation because I don't know the gravitational force that an object is feeling on the surface of Ceres. What I know is the mass of Ceres and the distance I am from its center of mass. So little g here is going to be equal to 6.67 times 10 to the negative 11th times the mass of Ceres, which is 7 times 10 to the 20th, divided by the distance I am from its center of mass. So that's going to be the radius of the planet, which is 500,000 meters squared. And when I throw that in my calculator, what I'll get is that little g is 0.19 meters per second squared. So if I were to take a box and go to Ceres, that's the rate at which that object would fall. And just to quickly show you the power of finding a gravitational field, I just want to add one additional bit to this problem. Let's find the force of gravity on a 100 kilogram object on the surface of Ceres. Now, previously, I would have had to say, f of g is gmm over r squared, and then I have to plug all those numbers in and solve for the force of gravity. But instead, I can just say that it's little g times the mass of the object, or 0.19 times 100, telling me that the force of the object is going to be 19 newtons. Now, when I'm just solving for the force on one object, of course, this is not particularly helpful because I really am still doing that legwork of multiplying gm and dividing by r squared. But say that I'm trying to find the mass of hundreds of objects at a specific point in space. You can hopefully see why in that situation, knowing little g would be very, very beneficial. So let's go ahead and talk takeaways. First of all, the gravitational force on an object is given by force of gravity is gmm over r squared, or in terms of little g, our gravitational force is given by g times the mass of the object we're putting in the field. So again, the gravitational force on an object is the field strength at the point of the space that the object is sitting times its mass. Second, massive objects, which are objects with mass, are going to generate gravitational fields of strength g equals gm divided by r squared, which we can also find by just dividing the gravitational force on an object in that field by its mass. So there you have it, folks. You now know how to solve problems involving gravitational fields. Give it a try on your own. Best of luck and happy solving.